In this video, we are going to talk about correlation and regression, which is topic 2 of Unit 5. So in the last section, we were looking at the relationship between two categorical variables. So we may have looked at the relationship between a person's political party and ideology, or whether or not they support GMOs and they're male or female. So the types of variables that we were looking at didn't have a number output, they had a category that they responded with. If we were looking at two numeric variables, then we have what's called bivariate numeric data. But in general, what you want to think about is you have two variables that exist on a number line when you plot them. So these two variables, what we want to do is analyze the relationship that they have between each other, if they have any relationship at all. So for example, height and weight may have a relationship with each other. In general, you might think that the taller a person is, the more that they weigh. However, there's lots of other variables that can be taken into account here, such as a person's, body type, whether or not they are, fit, whether they, gender, genetics, race, all sorts of things can come into play here. So, height and weight they probably have some sort of relationship between each other, but there's more to the story. And that's what we're going to find, is that there's basically always more to the story. However, we'll do a really good job at predicting a certain situation with just a few variables. So age and income, this one I think would be really all over the map, because things like experience, highest degree completed, whether or not they were competitive when they were getting their bid for their job, how many other applicants the job had available for that position. So there's lots more to this story, but in general, the older people are, the more money they make. If this was a person over time, that might be a lot more of a linear relationship. But age and income in general, I think could be all over the place for, different people. Square footage of a house and selling price. So these two I'm sure have some kind of relationship with each other, but there's lots of other things into account, such as number of bedrooms, number of bathrooms, the size of the yard, whether or not the kitchen is updated or not, whether, the house was, well made, the age of the house, the neighborhood that it's in, the location, the city, how aggressive the bidders were. So, in this situation, there's so many different variables we can think about, but how do we know which ones matter when predicting selling price? And how do we know if two populations, should be separated, or a data should be separated into two populations or not? So those are more advanced questions, but what we will find is that we'll do a really, really good job at modeling things just using a regular one variable input with one response. So this is where we get bivariate, because we're looking at two variables' relationship with each other. So we have two different types of variables. We have the response and the explanatory variable. I personally prefer to call this the independent variable, but lots of textbooks will interchange these two, or I'd say it's about 50-50 explanatory. I think independent makes less sense in terms of having the word explain what it means, but independent is kind of how we're used to describing things. So the response variable is basically our y, our output, and this is the variable that we're looking at predicting. So if we could just measure this, we have no reason to predict. So that's usually the question I ask myself first, is what is my response? Because usually the response can be identified, but the explanatory variable, that isn't always obviously an explanatory variable. So usually this one sticks out to me personally. The explanatory variable in general, however, we can measure. So we're looking to use the explanatory variable, or variables if you're doing regression with more than one independent variable. These are something that we can calculate in advance, and we want to eventually predict. So there's a few examples down here that I want to talk about, whether or not they are explanatory or the response. So the circumference of a tree and its age. So two questions. The first one is, which one do we want to predict? So sometimes maybe we want to predict the circumference. Maybe we don't have a measuring tool. But really we want to predict the age of the tree. So this is going to be the response variable here. The circumference is something that we can just measure. I mean, you can use a string and then use that for on a tape measure or something like that. So this is something that we can measure, and this is something that we want to predict, because unless you planted the tree and it's, you're like your favorite tree or something, unless it's that kind of situation, you probably don't know how old the tree is, but we can predict it pretty well based on its circumference. Yearly family income and amount spent at Christmas. So amount spent at Christmas is going to be our response variable, because this is something that could change. Lots of variation here will change by family, change by all sorts of things. And in a second, I'll talk about different things that could affect that. But one of the variables that may be significant in predicting the amount spent at Christmas could be yearly family income. So I'm sure there's going to be large differences between large gaps between, people that are, in the 1% and people that are, middle class or in the poverty level. I'm sure there's a big difference between those groups, but in general, within certain like income brackets, I'm sure there's a big variation here. So for example, I would want to know, my first question is, how much did they put on credit? So, I mean, just because you have a certain income at this point in the world, you can just kind of charge things on credit. Other things I'd want to know is how many kids are in the family. Are they, do they celebrate Christmas? That's definitely a valid question. So no matter what, we're never getting the full story, but we're still doing better than we were, which is usually, with the lack of statistics, not doing very well at all. We have usually no information. So the amount that Justin Bieber is Google searched in migraine headaches. So this is kind of maybe an oddball one, but just because, two things kind of, I don't know, just because you name two variables doesn't mean that you can make sense of one influencing the other or vice versa. So, I mean, I think on the solutions I put that this is kind of either you need more information to figure out what the heck is trying to be measured here, or, it could be either one. I don't think migraine headaches cause Justin Bieber, but what we're going to talk about in a second is that we're not looking at a causation. So correlation and causation are two different things. So Justin Bieber being Google searched maybe could have, a relationship with migraine headaches, because maybe people are hearing the Justin Bieber song and getting these vicious migraine headaches. And then lastly, BMI and time to walk 1 mile. So this is one of the ones that, depending on your situation, you may have an argument to change this one around. But in general, BMI is going to be pretty unchanging. So between, large periods of time, people's BMI will change in a drastic way. But in general, this is sort of a set amount. So what we would want to see here is if BMI, body mass index, and the time to walk 1 mile, do they have a relationship with each other? So now that we've talked about what our variables are, the next question is naturally to decide, okay, so what is the nature of this relationship and how strong is it? So two variables can go together, but they could have a very weak relationship. Two variables can go together and have no relationship at all, or the two variables could go hand in hand. But one of the major things I'm going to keep on emphasizing is that just because two things go together does not mean that one causes the other. So that's very important. Correlation is not the same thing as causation. So they can go together, but they might not cause each other. So the first thing that we want to do is make a graph. And this is going to be the absolute first step. I would never ever, I will do a hypothesis test and not make a histogram per se. However, I would never do a regression without making a scatter plot, because if you understand your data going into it, then you will really be able to understand the output. Now, the regression problems are very, very long, and the hypothesis test is a major piece, but it's also a small piece of the whole work that needs to be done. So it's really important to understand the scenario in general. So the explanatory or independent variable goes on the horizontal or the bottom axis, and we can have negative numbers and stuff, but I was just doing a generic L chart here. The response is the dependent variable, and that's going to go on the vertical axis. I have put in the letters X and Y. However, X and Y do not write them in this class, because what we want to do is we want to have, instead of X and Y, we want to have variables that fill in what they're actually doing. So instead of saying, X and Y, I'd want to say height and weight. Instead of saying X and Y, I'd want to say, amount spent at Christmas and the yearly family income. So don't say X and Y because that's really not doing anyone any favors, including yourself. But it is something that we are usually more used to is Y equals MX plus B. It's back. I do in general treat everything like it's pretty new. So that stuff, having knowledge of that will help, but it's not something that you need to be strong with before this topic. But again, it does help. So once you've created a scatter plot, the next few questions that you want to ask are, is the relationship positive or negative? Two variables are positively related, or they have a positive relationship if as one increases, the other one tends to decrease, or increase. So one increases and the other one increases. So one goes up, the other one goes up too. Two variables have a negative relationship with each other if as one increases, the other tends to decrease. And again, so we're going to put some little sample graphs here, but I really want to emphasize that it does not mean that one causes the other. It just means that you can measure the relationship between the two of them. So looking at, I put in 6 sample graphs, 3 for positive and 3 for negative. And the first pair is a very, very strong positive and a strong negative relationship. And the way that we measure this is that if we put a line through the dots fall either on or extremely close to the line. So this is evidence of a strong relationship. The next two show kind of a more spread out relationship. So this would be more of maybe a moderate. Honestly, this is still a pretty decently strong linear relationship. So this one is strongly positive or moderately positive, depending on what the output of the regression ends up being. And then this one would be, I'd say, strongly negative. We've got a little dot outside of the line here, but in general, they're pretty close. And then lastly, these two, in general, they kind of trend upwards and trend downwards, but it's not really like a very solid relationship. I think maybe this one's a moderate and this one's maybe a lower moderate or a weak relationship. So I'm just eyeballing these. We have a way that we officially measure the strength of the relationship. But in general, you read the graph the way you read words from left to right. So as I look at it from left to right, this graph is going up. Left to right, going up. If I look at this one from left to right, it's going down. So we're going to look at more of these, but what we really want is a very formal way to measure the strength of this relationship. So I'm going to do the grand reveal of my number line here. So the way that we measure the strength of the relationship between the two variables is by using this Pearson's correlation coefficient, which if you've taken another class that did regression, you may have talked about the R value. This is the same exact R value. We're doing regression in the same way you would have done in another class, but to a lot more detail. So first of all, the R value is between -1 to 1 inclusive, so that means -1 is possible and +1 is possible. If the R value is 1, there is a perfect positive linear relationship. If it's -1, there's a perfect negative linear relationship. And if the R value is 0, then there's no linear relationship between the two variables. However, we know that as sample data, we actually have a wiggle room that we use. So instead of just saying, 0, we would kind of need to say, okay, we're going to consider it no relationship if it's between a little bit below 0 and a little bit above 0. And things like sample size and other things like that will help determine how far does that range span. But the R value is going to tell us exactly what we want right now, which is how strong is the relationship. So I've broken this down a little bit more detailed than I think, could be used. But this is not, it's not, 100% solid. It's more of like a general cutoff. So it's not a strong cutoff. This isn't the same exact scale that you might see if you took a regression class with somebody else. But in general, these are the categories that would appear. So they might not say strong and very strong. They might have the whole thing from 0.6 to 1 just be strong. But I broke it down more because it's easier to put a few categories together than it is to break the categories apart, in my opinion. So if you have a positive relationship, you're going to have a positive R value. If you have a negative relationship, you'll have a negative R value. And so then being broken down into point 2 all the way from -1 to 1, they go weak, very weak linear relationship, and then very weak linear relationship on the negative end. In between point 2 and point 4, if the R value is in between those values, it's a weak linear relationship. -2 to -4, -0.2 to -0.4 is a weak negative linear relationship, and so on. So we're going to practice this in just a minute with an applet that I have. And this is up on your Moodle as well. So I would recommend trying a few of these by yourself. But when we get an R value, so we're going to run Stata and we're going to get a ton of output. When we get an R value, we are going to state the R value in a sentence. Lots of writing in this topic. So I would just, prepare to do a lot of writing. And so what we say is there is a, and then we pick which one up here it is. So strong, very strong, moderate, weak, very weak. Positive or negative, linear relationship between your two variables. So this order can be switched. It doesn't matter, but this is, just to have something written down here. That's the order that is specified, but this order is not important. So what I want to do is head over to the applet, and if you refresh this, you get different ones every time. So it's pretty cool. Okay, so I'm going to get one that has... Wow, those are close. Okay, so first of all, 3 of these have a negative relationship. Okay, so I'm expecting the R value to be negative. And so these are basically like multiple choice. There's no repeats. So, or like a matching, there's no repeats. So I didn't mean to click on that one. I can't unclick now. So this is going to be the positive one because there's only one positive R value. That's what these values are here. And then this is the only graph that increases as you go from left to right. And 0.91 is a very strong positive linear relationship. And this is, you could put a line right through this, and a lot of the dots would fall on the line. And the dots that don't fall exactly on the line are going to be pretty close. So I'm going to head over to this one. And so this one should be a pretty high negative relationship. So I'm liking this one right here for this because it's pretty similar to that R value, except for it's in the negative direction. And these two are pretty similar. They kind of look like they're just flipped around a mirror without these values that are kind of falling towards the ends. So now looking at these two here, they're both negative. This one is a little bit more kind of condensed, and this one is a little bit more scattered. So this is going to have an R value that's closer to 0. So looking at these two, 0.61 is still a strong negative linear relationship. So this still is good. It's still pretty good in its predictability. And then this other graph over here, this has got to be a little bit better, but not quite as good as this one. So first identify positive or negative. So let's check our answers. Yay, we got all smiley faces. Okay. So I would recommend doing this until you get all 4 of them right every single time for a few times in a row. Okay, so once you have a scatter plot, the next thing that you want to do is find a line that goes through it and figure out what that equation is. Well, if you've taken Business Calc 2, you may have done this by hand, but so this process is pretty long and complicated to do by hand. So that's why we are very lucky for our software. So you can use any type of equation at all, but we are only going to be looking at linear equations. It would be, I'd say, probably just as easy for us to look at quadratic, but I wanted to get really good at one type of regression, and quadratic isn't as popular. I find that a linear relationship occurs so frequently. It's definitely the one to know if you were to know one of them. So the method that Stata is going to use is called the least squares line. That's kind of just an FYI. And basically what it does is it minimizes the distance between whatever line you put in. So I could put the line down here if I really wanted to. So if I'm looking for the line that goes through here that is the absolute best, all right, I could put a line here, but it's not as close as it could possibly be to the most amount of points. So I like this second line for this one. I like this yellow line that I put in. Oops, that's too close to that color. So I like this purple line that I put in because it's closer to the, the center of all of these points, and there's less points that are scattered away from it. So if I were to estimate a line here, maybe that one. Maybe that one should go up a teeny bit. So I just like to think about, okay, well, this is the line. So I don't like that for that one. Maybe right around there, where the most amount of points, so the distance from the point to the line is as minimum as possible for every single point combined. But that's the way that it works. I would never want to do this for every individual value. I have done a few regression problems by hand, but in general, understand the concept and then go right to your software. So it's pretty realistic for statistics to end up using your software pretty frequently. So we're going to go back to our y equals mx plus b, our slope-intercept form of an equation. So this is y, our response variable, is equal to m, which is the slope of the line, that's our steepness, times x, the variable, which is the explanatory or the independent variable, plus the y-intercept, which we are going to use as the ordered pair 0, b. So this is the y-intercept, so this is where the line is sitting on the y-axis. That means your x value is 0 if you're chilling on your y-axis. So the way that we interpret the slope, honestly, this is one of the things that I think will take the most practice. But for interpreting a slope, for every increase of 1 in whatever your x variable is, the response goes up or down, depending on what your sign is, by whatever your average value of your slope is. This works, but it's not a very human version of this. So what I always do is I always write my slope as a fraction by putting it over 1. And then I like to write down the units or talk about the units that go with my my y, which is on top, and the x, which is on the bottom. So the slope formula is change in y over change in x. So that's what this triangle, it's a Greek letter delta, and so that means change in. So when I write the slope as a fraction with the units next to it, I say for every bottom per top in general. So depending on what your units are and what your problem is, you'll probably need to tweak this, but this is going to work in general for almost every single problem that we do. So we have 2 more pieces to this. There's a lot going on with regression, that's for sure. The problems are very long, and so for the final exam, any questions with regression, I definitely recommend that you write down all of this on your note sheet. I don't want you to memorize this, so it is up to you to make sure that you fill out your note sheet completely. So the coefficient of determination is the r value that we found previously squared. If there is only one x and one y, then you can just square the r value from previously, and that's going to be our case every time. Since we're taking a number from -1 to 1 and squaring it, that's going to be a value only between 0 and 1. And what it tells is it tells the amount of variability in the data that our model describes. So this is very, very vague until we actually get to an example. But we got so much going on, I like to go through it first, even if it is kind of vague. So the way we interpret this is our model accounts for blank % of the variability in the data. Other variables account for, and then 1 minus whatever this % is. So we can explain this percentage, and everything else is unexplained. So there are other variables that we haven't included in our model. And then lastly, this is honestly the kindest part of this whole thing. I don't think the rest of this is bad, but it definitely takes some, doing a few problems to get used to. We are doing an informal hypothesis test. My apologies, this is the calculator version. We're not going to be using that. We're going to be using one single output from this data to answer every single one of these questions. But we're doing an informal hypothesis test, and we're only going to include HO, H1, the p-value, how that compares to alpha, and the conclusion. So it's the same version as the informal hypothesis test that we did with the 2 population standard deviation test. Okay. So now let's actually get to an example. Actually, let's look at the reference tables first. So the reference tables has a lot of stuff here, but again, we're only going to be doing the informal version of this test. So HO and H1, this is how you get to it in Stata, but I do have a lot of instructions for Stata for this topic. But I want to mention again that this and the reference tables is very, very a small piece of the whole puzzle for regression. So a lot of it is understanding your situation and kind of analyzing and describing. I also want to mention that there's a document that has what we're doing step by step with screenshots. So if you don't want to, refer back to the video and try to catch the exact right moment, there is that. And so I also have all of my output for each of these individual practice questions in their own file. So again, if you don't want to scroll around on the video, I posted that as well so that you can just see the output that I've got instead of clicking through the video. Okay, so first of all, this problem is very long. It's a whole page. Most of it is going to be writing, and the hypothesis test is very little part of this. At this point, it's kind of nice to have that because we've been so heavy on the hypothesis testing. I also want to mention that I write really big, so I kind of ran out of space a lot, but I will be double checking for the final. I will have this be on 2 pages. But in general, you should be able to make this fit, but my handwriting is pretty big. So there's a data set that is in the topic 2 folder, and it's called Life Expectancy and Rate of Heart Disease by State. And this is actually the death rate of heart disease by state. And this has the life expectancy for each state as of 2014, and the death rate of heart disease is the number of people per 100,000 that die of heart disease. So I've already opened this data, and don't forget, it doesn't open the data, it just opens data. So I'm going to have a look first. So this should be in order from high to low for the rate of heart disease deaths. So Mississippi is first with 229.93 people per 100,000 per year that die of heart disease. And then last we have Hawaii with 136.69. So this is a big difference. So the other thing is that this is life expectancy per year. So what we expect is, but you have to think about this because there's a lot of different edges that you can take to this. So this is the rate that people are dying from heart disease. So in general, you might say, oh, well, the more people that are dying from heart disease, the lower their life expectancy. However, these people could be dying of heart disease at a very old age. We don't know that. So if there's no relationship at all, then we expect kind of like a flat line kind of with the dots scattered around a similar line. However, I do think there is going to be a relationship, especially since this has the highest rate of heart disease and the actual dead lowest life expectancy. And this is one of the highest, the highest life expectancy, and their rate of heart disease is not the very lowest, but it is lower. So we have a lower rate of heart disease actually right here with Minnesota. Okay, so looking at the questions here, we need to say which is our explanatory and which is the response variable. Explain why. I'm only going to explain why for the first one, but in general, it's kind of made to train you into picking your response. Roughly sketch the scatter plot, including the axis labels. Is the relationship positive or negative? Find the equation that models the data. Don't use X and Y. Use labels that make sense. Interpret the meaning of the slope in a sentence, interpret the y-intercept in a sentence, interpret the r and the r squared, and then determine if there is actually a true statistic linear relationship between the two variables. So even if this is like clear as day, you are always going to need to at least put this p-value So in a professional capacity, most of the time you only report the p-value for a hypothesis test. You say what your HO and your H1 are, what kind of test you're running, and your p-value. So doing an informal hypothesis test is actually pretty popular. So I'm going to start at the beginning, and I'm going to say that the response is life expectancy, and it's what we want to predict. And then the explanatory is the rate of heart disease deaths, which we can measure. So again, all of the steps that I'm doing are in a Moodle document for the data with screenshots, but I would try to follow along, because don't just try to follow the directions. Sometimes you can use these menus to help and sometimes you can't. So it really depends on each individual person and the actual software. So first we want to make a scatter plot. So you're going to go to this top one right here, two-way graph. Select that. And then it's going to pop open this menu here. So we need to define what our plot is going to be. And so you hit create. And so I want a basic plot, that's a scatter plot. And you indicate what your Y variable is, the life expectancy, and what your X variable is, which is the heart rate deaths, or the heart disease death rate. So when you hit accept, it defines this as plot 1, and what we actually need to do, because this just puts the dot on the graph, is we want to have the line go through as well. So if you hit create again, we now want it to do a fit, which sometimes the regression line is called a best fit line. So we're going to hit fit, and then we want to do a linear prediction. And then you just put in your Y and your X, and you hit accept. So I'm going to just hit the submit button, because what you're going to find is that it's sort of decently labeled, but you're going to start to be, it's more important than ever to have good labeling. So first of all, this has no label, and you should be labeling the entire graph in general. So that's why I'm hitting the submit button more often. So this is going to be the life expectancy by death rates of heart disease. So this is just one of the many things that you can name it. Oh, that's our x-axis. Oh, we want to put that here for title. And so then our x-axis already has a label because that was with the data. And the y-axis we want to be life expectancy. And you can put in years in parentheses. I mean, it's easier to have it than to have somebody not be sure what you mean. And so then I usually hit OK because now I'm done. So this looks like a pretty decent linear relationship. It's not as strong as the strongest one that we saw in the applet, but it definitely looks like a pretty strong relationship. So these people that are, dying of heart disease are in fact younger. Because if more people are dying with this, the life expectancy will go down if these people are in general younger than the average person that's dying. So the heart disease people that are younger than the average are bringing down the overall average. So this is going to be a negative relationship because we go down from left to right. And again, I kind of just speculated about the R value, but that's the thing that we want to eventually get from our data output. So I labeled this, I put a rough sketch on it. If I ask you to do a rough sketch, you don't need to, approximate exactly where the points are. Just get the gist of the shape. So I think I kind of did that. It's all right. So in general, it's got a similar steepness. That's really important because the steeper it is, the bigger the relationship is. Okay, so this is a negative relationship because as the death rate of heart disease increases, the life expectancy decreases. So these people are contributing to the lowering of the life expectancy. So the next portion of this is getting the regression output, which we don't have yet. So on your command window, you want to go to Statistics, Linear Models and Related, and then Linear Regression. And from here, all you need to do is enter in your dependent and independent variables. So we only have one independent variable, so we just need one variable here. When you hit submit, you get a bunch of stuff out. In interpreting this, there's a lot going on. I actually recommend, so let me open this back up just to show you, it's not that one. The instructions for setting up Stata also have instructions for interpreting. So we need 4 pieces of information from this table, and these are the 4 pieces that are color coded here. We make the R value from the R squared. So this is what I would refer to, because me pointing is going to be, not as straightforward as seeing this output highlighted and boxed. So we need an equation, and to get that equation, so this is our x variable, and constant, CONS is what constant, stands for constant, is the y-intercept. So the coefficient, if you remember from math class, is the number in front of the variable. So this is the y-intercept, and this is the slope. From this, we're also going to eventually need this p-value, so the top one. They're not always going to match. And we also need the r squared value. So those are the 4 pieces that we will need. I definitely, recommend writing down really specific information about this. So this one, r squared. That one's nice. But it's the top p-value, and this is how you make your equation of the line. So the equation is whatever our response is, which in this case is life expectancy, is equal to 87.3 minus 0.05 times the number of people per 100,000 that have died of heart disease. So I missed the word died in a lot of this. So instead of saying x and y, I said things that made sense to describe the variable, so life expectancy and number of people. And then interpreting the slope, again, this is the thing I think requires more practice. So 0.05 is the slope, and I always make it into a fraction by putting it over 1. And then I always remind myself that, okay, a slope is the change in y over the change in x. So this says, and then for every, bottom per top. So the x is the rate of heart disease per 100,000. And then the y is the life expectancy in years. So for every 1 person per 100,000 that dies from heart disease, the life expectancy goes down by 0.05 years, okay, because this is a negative. So it goes down by 0.05 years. The y-intercept is 0, 87.3. And so this is x comma y. And so this 0 is for the heart disease, number of people, and this is the years that they live, the life expectancy. So if 0 people per 100,000 died per year from heart disease, so this is kind of like in theory, and it's technically extrapolating because we didn't have anyone at all that was even close to 0. So this is not always able to be relied on, but it's more of kind of a theoretical thing. So if 0 people per 100,000 died per year from heart disease, life expectancy would be 87.3 years. So if we did have a state that had, no heart disease at all, this is what we would expect. Although if they had no heart disease, they would probably have lots of other, situations that they didn't have anything of. So they might be their own kind of population and might not belong in this data. So G, interpret the meaning of the R value in a complete sentence. Well, what we need first is the R squared. So the R squared value was 0.7480. So we need to square root this value in order to get the R value. So 0.8649 is the R value, and we know from up here that it should be negative. So Stata doesn't care if it's positive or negative, that's up to your interpretation. So what we would say here is that because 0.86 is between, so 0.86 negative though, so negative 0.86, it's between negative zero point 0.8 and 1, then we say there is a very strong negative relationship between life expectancy and the death rate of heart disease. The R-squared value is interpreted as 0.7480, and that means that the death rate of heart disease accounts for 74.80% of the variability in the data. So what this actually means is that this scatter plot here, the reason why we're able to explain the difference, 74.80% of the distance that these values are away from the line. The other variables account for, so what I would do here is say, okay, 100 minus 74.8, 25.2% is explained by other variables. So it could be something like obesity rate, the rate of smoking. So there are other variables that we could drop into our regression to end up getting a line that fits better, which I know sounds like kind of crazy, but it's not something you could look at in a two-dimensional way. So eventually you'll be 3D, 4D, all the way on up to however many variables you have, that many dimensions minus, that many variables minus 1. So here we have a line that goes through pretty decently. There's some variation, meaning there's some variability where the dots fall away from the line. And so that distance is explained by other variables. But we have explained 74.8% of the way that the dots don't land on the line, which is pretty damn good. So this one variable alone, and I did compile this data from CDC data. So this one variable alone explains the change in the death rate by 74.80%. It doesn't cause the death rate to decrease per se. In this case, it could be more causation than anything. However, we never determine that. We only decide, hey, these two things go together, and we give it to somebody who's an expert in, life expectancy and stuff like that to figure out. So lastly, we have perform an informal hypothesis test to determine if the relationship between the variables is significant. So what we want to know here is we want to make sure that we have a slope that is statistically this angle instead of being a flat line straight across. So, I mean, at this point, this line is so far from being straight across that I would be absolutely shocked. However, what we do is we say, okay, let's pretend the slope is 0, completely flat line. How crazy is it for this to happen? Well, with an R-squared as big as we have, it's pretty unusual for that to happen. But when we ran the hypothesis test, which we got from our data output, this one right here, we end up getting a p-value of 0, which is, less than 0.05, so we reject HO. And then we say that there is a statistically linear relationship between those two variables. So the other two problems follow the exact same process, but there's a lot of information. So I would definitely make sure that you go through both of these before attempting the learning quiz. So the next problem I'm just going to introduce. So this is real data, and it's the 100-meter freestyle Olympic winning time in seconds for women. So this is the women's time. This is the year that that record or that Olympic meter was set. So one thing you do with time data only, so see how it says input your data such that 1912 is year 0, 1920 is year 8, etc. You want to phrase this like this because this was the first Olympics. So we want to model what happens the year since the first Olympics. So this was 8 years later. If you think about what would happen in between here that an Olympics wouldn't happen, well, there was a world war in here. And the next time an Olympics didn't happen, it was also because of a world war. So I'm just FYI, something I didn't really think about how the Olympics wouldn't have happened during world wars until this question. I mean, it makes sense, but I just never thought about it. So this here would be 8, because we're calling this 0. So this is 8 years after 1912. This is 12 years after 1912, and we only do this with time data. So when we put this in here, I wouldn't put 1912 at all. I would put 0, 8, 12, 16, and so on. And so this last one I believe should be 76. Yeah, 76. And so that would be your final number here. And so then these values you can leave as they are. Time data is really popular. It's not something that I emphasize specifically, but I always make sure that I do one that has time data in here because it is something that will happen to you, if you're modeling something. And this might give you ideas to change your project or something like that. If that's interesting to you, up to you. But just please let me know. The answers, everything is all uploaded here. If you have any questions, please send me an email. But this one is going to be, I think, a little bit more time consuming because this is the 3-day topic in class. So it's definitely something that we spend more time on in class. So it should be a topic that you spend a little bit more time on at home.